Here, let's consider for the zero field case. Zero field case means that deep inside a superconductor, because in the deep inside a superconductor there is no magnetic field inside a perfect superconductivity, and also we already derived the Ginzburg-Landau equations, and we will use the Ginzburg-Landau equation in the superconducting state. And here. Three, zero field case. Zero field case means that deep inside sample, inside a superconductor. Here, because deep inside a superconductor there is a magnetic field inside the sample, and B field, zero inside the sample, inside the superconductor. It means that the vector potential also zero in the zero field case, and the homogeneous boundary condition means that Laplacian phi equal to zero, and it corresponds to a deep region inside a superconductor. In the case that the super electron density does not vary with the position, and homogeneous order parameter. It means that homogeneous boundary condition, homogeneous order parameter. And because there is no magnetic field from the Ginzburg-Landau equations, and there is no magnetic field cases, and also if we neglect because vector potential equal to zero, and also there is no if we neglect the kinetic energy term, and the superconducting free energy can be written down as the normal state gives free energy plus a phi square plus 1f b phi to the 4, and in this case A is negative, B is positive below Tc, and in this case this free energy is the without magnetic field, and the zero magnetic field case, it is a zero field case. Therefore, we should find that the minimized free energy, and here from the previous, let's derivative phi star by keeping phi is constant. Then in this case, and a phi plus, because this free energy can be written down as Gs is the Gn plus a phi star phi plus 1f b phi star phi star phi star phi, and therefore from this equation, and also a phi plus b phi square phi equal to 0. In normal state means that there is no superconducting order parameter, therefore phi equal to 0. But in superconducting state, the phi order parameter is not 0, and there is a finite order parameter, therefore the phi can be cancelled with each other from this equation, and therefore phi square is that minus a over b. And also we assume that a is minus, and the previous time we assume that a is a0 t over tc minus 1, and the b equal to b0. We assume like that, and therefore it is this absolute value of b. Therefore phi square is the positive value, and also therefore from under this assumption, and it is at a0 over b0, it is 1 minus T over Tc. And here, therefore, this A0 and B0 are positive value, and therefore, when you think that it is a linear relationship, linear dependence of temperature near Tc value. Therefore, when you think about that, the order parameter, with temperature dependent order parameter case, in many cases, it is temperature dependent order parameter, and the Tc, in the Tc there is a finite order parameter, and also near Tc value it is a linear value, and also the y-intercept is that zero temperature case, it is A0 over B0. The y-axis is that order parameter square. Then, but in real state, it is not linear at a low temperature. It is therefore, in many cases, there is a finite order parameter square, phi0 square, and there is like this in real cases. Okay. In quantum mechanics, the wave function square wave function is corresponding to the electron density. But like that, the super electron density can be write down order parameter square. Therefore, in order parameter square is that A0 over B0 1 minus T over Tc. That's why there is an superconducting state develops near below Tc value, and when from this assumption, and the superconducting state is that normal state plus A, because it is a phi square. The first term is a phi square, is that minus A over B and plus 1fb, and it is phi square phi to the 4, and therefore it is A over B square. Then it is Gn minus A square over B plus 2b A square. Therefore it is that Gn minus A square over 2b. Therefore, from this interpretation, also we can think that it is a Gn minus 1/2, and A0 square over B0, it is 1 minus T over Tc square. Therefore, the superconducting free energy is lower than the normal state free energy as much as this value. Therefore, this value is the condensation energy. Condensation energy is that lowering energy from the normal state, and therefore it is 1/2 A square over B, and it is a condensation energy can be correspond to the BC square over 2 mu 0, and it is critical magnetic field. It is corresponding to the critical magnetic field. Also, this is a deep inside sample, and let's think about that zero field case near superconducting boundary. Near superconducting boundary. In the superconducting boundary means that there is a superconducting state, and also it is a vacuum. Or the normal metal. And here in this case, in the deep inside sample, the order parameter is homogeneous, but in the surface, the order parameter is not homogeneous, because super electrons superelectron, there is a penetration depth, and the superelectron flows in the interface state. There is a penetration depth, and there is a superelectron flows near the interfaces at the boundaries. Therefore, in this case, and zero field case is an inhomogeneous boundary condition, but it means that gradient can exist, and also from the phase vector and exponential I zeta, it is order parameter, and zeta is the phase independent of position, and also we assume that and phi star del phi equal to phi del phi star. It means that here phase vector, then the del means that phase vector, because phi is the real value and the gradient the different thing of gradient is the phi zeta variable, and therefore phase zeta is independent with the position. Therefore, from the first Ginzburg-Landau theory, Ginzburg-Landau equation with the absence of magnetic vector potential, and first Ginzburg-Landau, the first Ginzburg-Landau equation is that h bar square over 2m star del square phi, it is kinetic energy, and the kinetic energy plus a phi plus b phi square phi equal to 0. It is first Ginzburg-Landau equation. And let's consider for the one-dimensional case like that h bar square over 2m star d square phi dx square plus a phi plus b phi square phi equal to 0. And also here a equal minus a below TC case. Then we should prove that we should have get the solution on this differential equation, and also in this case we should use that any trick. And what kind of trick? It is a substitutional effect, substitutional method, and let the phi can be write down as a square root a over b f. Then let's substitute this equation. Then the first term minus h bar square 2m star, and so dd square phi means that a over b 1/2 d square f dx square minus a phi is the square root to b a to the 3/2 f plus this term shows that b and b square phi square is that a over b, and phi is that a over b 1/2. Therefore it is that square root to b a to the 3/2 f cube should equal to 0. Let's divide in both sides by using this term, then minus h bar square to m star a d square f dx square plus f 1 minus f square equal to 0. And this is coming from the first Ginzburg-Landau equation. We solve the first Ginzburg-Landau equation without applying magnetic field. And also here, let's define the dimensionless variable. Eta equal to x of chi square, x of chi, and here the chi square is the, it is chi square, h bar square over 2m star a. Then we can calculate ddx is that d eta dx. Then d eta dx is that 1 over psi d eta. Therefore, d square dx square is that 1 over cosine square d square d eta square. Therefore, let's substitute this equation, and because it is cosine square, and d square dx square is that 1 over cosine square. Cosine square cancel with each other. Therefore, it is that the equation becomes d square f d eta square plus f 1 minus f square equal to 0. And the first Ginzburg-Landau equation becomes this equation. It is the nonlinear differential equation, a little bit difficult to solve, straightforward. And here the solution is that the solution have a function of hyperbolic tangent y over square root 2. And we can confirm this is a solution. df d eta is that 1 over square root 2 secant hyperbolic square at y over square root 2, and d square f d eta is that minus 1f and 2 secant hyperbolic y over square root 2, and also scale differentiation of scale secant hyperbolic is that secant hyperbolic and tangent hyperbolic. And also 1 minus f square is that 1 minus hyperbolic tangent, then it is secant hyperbolic square y over square root 2. Therefore, when you substitute this equation, and also d square f d eta square is the minus secant hyperbolic square y over square root 2 tangent hyperbolic y over square root 2, and as f is that plus hyperbolic tangent y over square root 2, and also 1 minus f square is that secant hyperbolic square y over square root 2. Therefore, it is a 0. Therefore, it is that it is the solution on this equation. Therefore, the solution on the first Ginzburg-Landau equation is that the phi is that infinite phi hyperbolic tangent x over square root 2 psi, and here phi infinity is that A over B half. And anyway, I will summarize again. And we dealing with superconducting boundary, zero field case, because in this case, it is not homogeneous. Therefore, the order parameter is not zero inside in near the grain boundary, and also, but we assume that this condition, and this condition indicates that phase vector is independent with the position, and therefore we starting from the first Ginzburg-Landau equation, because second Ginzburg-Landau equation is coming from the vector potential, and also, but in our case vector potential equal to 0. Therefore we only consider for the first Ginzburg-Landau equation. And anyway, to solve this Ginzburg-Landau equation, and we substituted somehow case, and the solution, we find that the solution is the hyperbolic tangent, and the hyperbolic tangent is the final solution. And here, but the f is that f is like this. Therefore it is that hyperbolic tangent multiply square root a over b. Then the square root a over b, we denote that phi infinity. And therefore in this case, and for x close to 0, x close to 0 means that at the interface, and the order parameter close to 0, and x infinity means that and there is very long distance inside the sample, and in this case phi goes to infinity. It means that the superconducting state is very stable. And also in this case, from the second Ginzburg-Landau equation, we know that the J value is that minus 2m star IH bar E star phi star del phi minus phi del phi star minus E star square over m star a phi equal to 0, because we assume that it is 0, and also there is no vector potential, therefore the current is 0. It is reasonable because if there is no magnetic field, and there is no current in the superconducting state, even the low Tc, then the critical current can be generated by only when we apply the magnetic field. Okay, it is consistent to the conventional wisdom.